Natural gas powers our homes and industries. But have you ever wondered where it comes from? The journey of natural gas begins millions of years ago. Imagine a time when dinosaurs roamed the earth. Lush swamps and forests covered the land. Over eons, the remains of ancient life, plants and animals accumulated in these environments. These organic materials became buried under layers of sediment. Sand, mud, and rock piled up over time, creating immense pressure and heat. The organic matter trapped in an oxygen-deprived environment undergoes a remarkable transformation. The transformation of organic matter into natural gas is a slow and intricate process. It is driven by microscopic organisms called microorganisms. These tiny decomposers break down the complex organic molecules. They release methane as a byproduct. Methane, a simple but potent hydrocarbon, is the primary component of natural gas. Over millions of years, this methane gas accumulates and becomes trapped within the Earth's crust. These geological formations act like giant underground reservoirs, storing vast quantities of natural gas. Today we tap into these ancient reserves to meet our energy needs. Picture a time long before the dinosaurs, when Earth's continents were still forming. Vast, shallow seas covered much of the planet, teeming with primitive life forms. As these life forms died, their remains settled on the seabed, forming layers of organic material. Over time, rivers carried sediments from the land, depositing sand, silt, and clay over the layers of organic matter. This process of sedimentation continued for millions of years, burying the organic matter deeper and deeper within the Earth's crust. Trapped beneath layers of sediment, the organic matter entered a realm of darkness and increasing pressure. Here, in the absence of oxygen, a different kind of life thrived: anaerobic microorganisms. These tiny decomposers, invisible to the naked eye, played a crucial role in the transformation of organic matter into natural gas. The anaerobic microorganisms, in their quest for energy, broke down the complex organic molecules in the buried remains. This decomposition process, known as anaerobic digestion, released various gases as byproducts. As the layers of sediment continued to pile up, the pressure on the buried organic matter increased dramatically. This pressure, combined with the heat from the Earth's interior, acted as a catalyst, accelerating the transformation process. Over millions of years, the organic matter underwent a series of chemical reactions, slowly converting into hydrocarbons. Methane, being a relatively stable and light hydrocarbon, rose through the porous layers of rock, accumulating in pockets and reservoirs. These trapped deposits of methane, formed over eons, became the natural gas reserves we tap into today. Over millions of years, the Earth's surface undergoes constant change. Mountains rise and erode, rivers carve valleys, and oceans advance and retreat. Throughout these dynamic processes, sediments like sand, silt, and clay are carried by wind and water and deposited in low-lying areas, forming layers upon layers of geological history. These layers over time create vast depressions known as sedimentary basins. As organic matter gets buried deeper within these basins, it's subjected to increasing pressure and temperature, the key ingredients for the transformation into natural gas. The weight of the overlying sediments compacts the organic rich layers, squeezing out water and concentrating the hydrocarbons. Not all rocks store natural gas equally. Shale and sandstone are ideal reservoirs, trapping gas for millions of years. Shale's low permeability prevents gas escape. Sandstone's pores hold significant gas volumes. Traps formed by tectonic forces seal the gas. A global jigsaw puzzle distribution of natural gas deposits. Natural gas deposits are not uniformly distributed across the globe. Instead, they're concentrated in specific regions, often associated with ancient sedimentary basins and favorable geological formations. From the vast shale formations of North America to the gas-rich fields of the Middle East, each deposit tells a unique geological story. Geologists and engineers work together to identify potential gas-bearing formations, analyze rock properties, and map underground structures to pinpoint the best locations for drilling. This global quest for natural gas, driven by our ever-increasing energy demands, highlights the importance of understanding the geological playground where this valuable resource is found. To understand natural gas, we need to delve into the realm of molecules, the building blocks of all matter. Natural gas, in its essence, is a mixture of hydrocarbons, with methane or CH4 reigning supreme as the most abundant component. Methane, a simple yet powerful molecule, consists of one carbon atom bonded to 4 hydrogen atoms. This simple arrangement of atoms holds the key to unlocking a tremendous amount of energy. When methane burns, these carbon-hydrogen bonds break, releasing energy in the form of heat and light, fueling our homes and industries. Hydrogen, the lightest element with its single proton and electron, readily forms these connections. While methane is the star of the natural gas show, it's not alone in this underground energy ensemble. Other hydrocarbons like ethane or C2H6, propane or C3H8, and butane or C4H10 join the mix, each with its own unique properties and uses. These hydrocarbons, with varying numbers of carbon and hydrogen atoms, form a family of molecules known as alkanes. Ethane, with its 2 carbon atoms, finds its niche in the production of plastics. Propane, a versatile fuel, powers our grills and heats our homes. Butane, easily liquefied under pressure, fuels lighters and camping stoves. The transformation of organic matter into hydrocarbons is a slow process. It unfolds over millions of years, deep within the Earth's crust. Immense sediment layers press down, squeezing the buried organic matter. Pressure and heat create a subterranean pressure cooker. Organic molecules undergo chemical reactions. The longer the burial, the more methane forms, the key component of natural gas. The journey from organic matter to natural gas involves a fascinating intermediate stage, the formation of kerogen. Imagine kerogen as a complex, waxy substance, a halfway point in the transformation process. As the organic matter gets buried deeper and subjected to increasing heat and pressure, it loses its oxygen and hydrogen atoms, becoming more concentrated in carbon. This process, known as diagenesis, transforms the organic matter into kerogen, a precursor to hydrocarbons. As the temperature and pressure continue to rise, kerogen undergoes a process called catagenesis. During catagenesis, the kerogen molecules break down further, releasing hydrocarbons, primarily methane. For decades, vast reserves of natural gas lay trapped within shale formations, tantalizingly close yet frustratingly inaccessible. Shale, with its low permeability, held the gas captive, preventing its easy extraction using conventional drilling techniques. Then came a game-changer: hydraulic fracturing, or fracking, a technology that revolutionized the energy industry and unlocked a treasure chest of previously untapped natural gas. Imagine drilling a well deep into the earth, reaching the gas-bearing shale formation. These fractures, like tiny cracks in a dam, release the trapped natural gas, allowing it to flow up the well bore to the surface. Environmental concerns arose, raising questions about the potential impact of this technology on our precious water resources, air quality, and the delicate balance of ecosystems. Fracking requires vast amounts of water, and critics argued that the chemicals used in the fracking fluid could contaminate groundwater aquifers, potentially impacting drinking water supplies. Another concern was the release of methane, a potent greenhouse gas, during the fracking process. Methane leaks from wellheads, pipelines, and other infrastructure could contribute to climate change, offsetting some of the environmental benefits of natural gas compared to other fossil fuels. The debate over fracking's environmental impact intensified with reports of earthquakes in areas with active fracking operations. The injection of fluids into the Earth's crust, some argued, could trigger seismic activity, raising concerns about the potential for induced earthquakes. Scientific studies were launched to investigate the link between fracking and earthquakes, seeking to separate fact from fiction. While fracking itself does not directly cause large-scale earthquakes, the disposal of wastewater from fracking operations, often injected into deep underground wells, can increase pressure along fault lines, potentially triggering smaller earthquakes in areas prone to seismic activity. The debate over fracking's future is likely to continue as we grapple with the need for energy independence, economic development, and environmental protection. Finding a sustainable path forward requires a delicate balancing act, weighing the benefits of natural gas production against the potential risks to our environment and communities. Stricter regulations, rigorous monitoring, and transparent data sharing can enhance public trust and ensure that fracking operations are conducted responsibly. Ultimately, the future of fracking depends on our ability to innovate, regulate, and collaborate to harness the energy potential of shale formations while safeguarding the planet for future generations. Global gas giants, from shales to sands, natural gas reserves, those vast underground reservoirs of this valuable energy source, are not evenly distributed across our planet. Instead, they're concentrated in specific regions, often shaped by millions of years of geological processes. These reserves, like hidden treasures, lie buried beneath continents and oceans, waiting to be discovered and harnessed to meet our growing energy demands. North America, once heavily reliant on energy imports, has emerged as a natural gas powerhouse, thanks to the shale revolution. The Marcellus Shale, stretching across Pennsylvania, West Virginia, and Ohio, holds vast reserves of natural gas, transforming the energy landscape of the United States. Environmental footprints, a price for energy. While natural gas burns cleaner than coal and oil, emitting fewer greenhouse gases and pollutants, its extraction and production still leave an environmental footprint. Land use change is a significant concern, particularly in regions where natural gas extraction activities overlap with sensitive ecosystems or agricultural lands. The construction of well pads, pipelines, and access roads can fragment habitats, disrupt wildlife migration corridors, and alter the visual landscape. As the world transitions towards a cleaner and more sustainable energy future, natural gas is often touted as a bridge fuel. Its lower carbon footprint compared to coal and oil, combined with its versatility as an energy source for electricity generation, heating, and industrial processes, makes it an attractive option for a gradual shift away from fossil fuels. When the sun isn't shining or the wind isn't blowing, natural gas power plants can quickly ramp up electricity generation, ensuring grid stability and meeting energy demands. The key to a sustainable energy future lies in finding a balance between utilizing natural gas as a bridge fuel while aggressively pursuing the development and deployment of renewable energy technologies. This balancing act requires a multi-pronged approach involving technological advancements, policy initiatives, and a shift in consumer behavior. Investing in research and development of carbon capture and storage technologies is crucial to mitigate the environmental impact of natural gas. Furthermore, implementing stricter regulations and monitoring of methane leaks throughout the natural gas supply chain, from wellhead to pipeline to end user, can significantly reduce greenhouse gas emissions. The journey of natural gas, from its ancient origins to its role in our modern world, is a testament to the incredible forces that have shaped our planet and the ingenuity of humankind to harness its resources. We've journeyed back in time, witnessing the slow, intricate processes that transformed the remains of prehistoric life into this valuable energy source. We've explored the depths of sedimentary basins, those vast underground reservoirs where natural gas lay dormant for eons, trapped within layers of shale and sandstone. From the depths of the earth to the pipelines that crisscross our continents, natural gas has emerged as a cornerstone of modern civilization, fueling our homes, industries, and economies. As we stand at the crossroads of a changing climate and rising energy demand, the role of natural gas is evolving. It burns cleaner than coal and oil, emitting fewer pollutants. However, extraction impacts the environment. Fracking raises concerns about water contamination and methane leaks. We need a balanced approach, recognizing natural gas as a bridge fuel while accelerating the shift to renewables. The transition to a sustainable energy future requires technological advancements, policy initiatives, and a shift in consumer behavior. Investing in research and development makes renewable energy more efficient, affordable, and accessible. Solar, wind, hydro, and geothermal sources are key to a sustainable future. Policies should incentivize renewable energy, promote efficiency, and phase out fossil fuel subsidies. Carbon pricing mechanisms can make renewable energy more competitive. The future of energy is about creating a diverse and resilient mix that meets our needs while safeguarding the planet. This transition requires a collective effort, a shared responsibility among all of us. By embracing innovation and collaboration, we can ensure a sustainable future. If you like this content, please share, like, comment, and subscribe.